Hello students, and welcome to section 5.5, multiple angle and product sum formulas. We're going to go ahead and take a look at multiple angle formulas to start, particularly the double angle formulas. We have the sine of 2u, cosine of 2u, which has three versions, and then the tangent of 2u. Let's go ahead and take a look. In terms of the sine of a double angle, sine of 2u, now we have seen this in the past in which maybe we're solving for u, and we will still do that, but actually the sine of 2u has another variation that we're going to interpret, and that will be 2 sine of u, cosine of u, so just single angles for those. With the cosine of a double angle 2u, it's equal to cosine squared u minus sine squared u. But you can actually derive the other two, as you see. Let's say if you were to replace sine squared with 1 minus cosine squared, you can actually get 2 cosine squared minus 1 from that. Or if you take cosine squared and turn that into 1 minus sine squared, you can derive the third version, which is 1 minus 2 sine squared u. The third equation, or third formula really, we're going to take a look at is the tangent of 2u, which is 2 tangent u all over 1 minus tangent squared u. The other version, I guess, we can write here as well as what we've seen in the past for tangents in the previous sections. We can actually write this as the sine of 2u over the cosine of 2u. That may prove more powerful in terms of what type of problem we're looking at, or we could just stick to the basic formula and see how that goes. We'll take a look and see when that will be the case. Example 1. Solve sine of 2x minus cosine of x equals 0. Now we are going to go ahead and do this between 0 and 2 pi. And we'll go ahead and start the process looking at first the sine of 2x. And again, noting that because this is a double angle, we'll be able to write this using our new formula as such. 2 sine cosine. And then we'll just rewrite minus cosine of x. And what we have here, if you can see, we've got a GCF. Our GCF, right, greatest common factor between the two terms, happens to be cosine. So we'll factor out that cosine. And what we're left with from the first factor is 2 sine of x, and from the second, just minus 1. Still set equal to 0. Turns out, as what we've seen in the past, we have two factors which we can easily simply set equal to 0. And I'll do the quick analysis saying that if I add 1 and divide by 2, sine of x there equals 1/2. So cosine of x equals 0, and sine of x equals 1/2. Then we start thinking about what angle or angles have an x-coordinate of 0. Right, that's what the cosine tells us. We're thinking that, well, gosh, pi over 2 and 3 pi over 2. Those two angles have an x-coordinate or cosine of 0. We look at the other equation, we solve for x, in which again we think, okay, what angle or angles have a y-coordinate, which is what sine is, of 1/2. We think of our unit circle, and those two angles would be pi over 6 and 5 pi over 6. So this particular problem has 4 answers, in which if we were to graph, the left side of the equation is y1, which we've seen in the past, and the right side is y2. These two functions will intersect at these 4 intersection points. Let's move on to example 2. Sketch the graph of y equals cosine of the fourth minus sine of the fourth of x on the interval, again, 0 to 2 pi. And let's actually make that little correction. That should be a parentheses there. So what we'll go ahead and do is we'll talk about maybe implementing one of these new formulas, but first rewrite the question as such. And part of the reason why I want to rewrite my equation is in order for me to incorporate one of the new formulas, and I think you might already kind of be able to see what's about to unfold here. I want to try to see if I can use a double angle formula, but if I were to convert sine to the fourth into sine squared squared, a Pythagorean identity will actually be utilized in that parentheses quite nicely, which you'll see in the next step. So cosine to the fourth minus the quantity 1 minus cosine squared. Now that whole thing is still squared, so be careful, right? We're again using the Pythagorean identity we're familiar with. 1 minus cosine squared is sine squared, but again, that whole thing is squared. Let's continue. The nice thing is I do have cosines exclusively in this particular problem, so I'll have to simplify. Let's see how that's going to unfold. So I have cosine of the fourth minus, and notice two binomials multiplied appropriately because I'm squaring 1 minus cosine squared times 1 minus cosine squared. So if I continue, I've got cosine of the fourth minus, and I'll FOIL. So first, outside, inside. So I have 2, technically, negative cosine squared. So negative 2 cosine squared x. And then negative cosine squared times negative cosine squared. That's positive cosine of the fourth x. Now I will have to distribute that negative, but I can kind of foresee here that when I do distribute that negative, my cosine to the fourths will actually subtract out, leaving me with the following. Distribute the negative, turning this into a negative 1. Distribute the negative, turning this into a positive 2. So it's actually 2 cosine squared minus 1. Which, if you remember back at the top of my notes, that does in fact end up being a double angle for cosine of 2u. It's equal to, one version, 2 cosine squared minus 1. So we'll go ahead and rewrite this as exactly what we saw. So cosine 2x, and that's the conversion. That's converting cosine of the fourth x minus sine of the fourth x as a little bit more familiar function in terms of us needing to graph. I'll just write y equals here. But we can graph this thinking about what we learned in chapter 4, where we remember that the period of a cosine function is 2 pi divided by b. And because my b value is 2, the period is pi. And remember, we're asked to graph this function from the get-go. I'm actually going to do a quick graph and analysis of that graph using exactly what we found, but what we're typically used to using for a period. We'll go ahead and make 2 full periods. 1, 2, 3, 4. Let's actually make that a little bit smaller. 1, 2, 3, 4. So that's 1 period at pi, and then 1, 2, 3, 4, 2 pi. So we are going to actually graph from 0 to 2 pi, again, as they initially had asked. But it is 2 periods because, again, as we saw back here, our period is pi, not 2 pi. And I guess I can highlight that. Because it's less than 2 pi, we know that it is actually a horizontal shrink. Something, again, from chapter 4 to reflect upon. If we were to kind of just go through the process, starting with 0, and this is pi over 2, so 1/2 pi. This is 2/2. This will be 3 pi over 2, as we recall. We can go through the process, plugging in 0, cosine of, well, 2 times 0, that will be just cosine of 0, which is 1. And if we plug in pi over 4 times 2, that's actually pi over 2. So the cosine of pi over 2 is 0. If we plug in pi over 2, 2 times pi over 2, that becomes pi. So cosine of pi, that becomes negative 1. Plugging in the next increment, so I was actually plugging in fourths, 1/4, 2/4, 3/4. So 3 pi over 4 times 2, that's simply 3 pi over 2, the cosine of that being 0. And then pi, if we plug in pi, cosine of 2 pi, well, that's just 1. So this reflects, again, just one period. Another full period would have the following shape to it. Again, this is pi. If we were to look at it in terms of fourths, we could say 4 pi over 4, then 5 pi over 4 would be at 0, 6 pi over 4 at negative 1, 7 pi over 4 at 0, and then lastly 8 pi over 4 would be up at 1. So your function, with, again, 2 full periods graphed, because again they said 0 to 2 pi, looks something like this. Let's move on to the next example, next page. Example 3. So it says, given the sine of x equals 12/13 and pi over 2 is less than x, which is less than pi. Find the sine of 2x, cosine of 2x, and tangent of 2x. So we'll go ahead and try to think about really right away here where this particular angle will fall. Because they tell us that x is between pi over 2 and pi, we're looking at a second quadrant angle. And that's important. And we do reflect upon where that angle falls, but then in turn where the double angle will be. We'll need to have that perspective to start with. So we'll draw our right angle, right triangle, and right angle there. There's your angle x. We do know that the sine of x to start with, opposite over hypotenuse. So opposite of x is 12, there it is, and the hypotenuse 13. This ends up being a 5, 12, 13 right triangle. We could use the Pythagorean theorem to find b. But again, because it's a 5, 12, 13, I can just simply fill in 5. But be careful. Make sure that it's negative, not positive. Because it's in the second quadrant, we know that the cosine is negative. And we also can write the ratio for cosine right now as adjacent over hypotenuse, so negative 5/13. So we're going to go ahead and find the sine of x, cosine of 2x, and the tangent of 2x, all of which will require the use of one of our new formulas. The sine of 2x, there's only one version we can use, that's 2 sine x, which is 12/13, times cosine of x, which is now negative 5/13. And that particular result, if we multiply the denominators, we have 169. And if we multiply the numerators across, that becomes negative 120. And that's not reducible, so that's our answer for the sine of the double angle. Take a look at the sign on that particular value. That's a negative. Thinking about where our angle is from the beginning, that's in the second quadrant. So if we multiply that angle by 2, that angle will likely land in quadrant 3 or 4, but it's going to have a negative y-coordinate. Cosine of 2x, we'll go ahead and use the formula by taking the cosine of the angle x squared. Notice I'm squaring the whole quantity, and then that minus the sine of the angle x, that quantity squared. If we do that math, do the analysis, we'll have 13 squared and 13 squared, which if we subtract has that common denominator of 169, and the numerators 25 minus 144, negative 119. That particular ratio is also negative, so if you actually think about how both of these are negative, when you double that angle in the second quadrant, it actually lands in the third quadrant. We could actually find angle x. We won't do that, not on this particular example, but if you did, you would find that it would nicely land in quadrant 3. And our answers prove that just simply with their signs. Last but not least, for the tangent of 2x, so we'll use sine of 2x, which we got from the very first part of this, so negative 120 over 169, divided by the cosine of 2x, the second part, so negative 119 over 169. And that simplifies quite nicely where the 169's divide out. Remember, dividing by a fraction is the same as multiplying by the reciprocal, so those do divide out nicely. In the end, we end up with the following ratio, 120 over 119. And again, not surprisingly, this particular ratio does end up being positive. A third quadrant angle, which is again what this double angle will be, a third quadrant angle, will have a positive tangent. That concludes part 1. We will continue part 2 at a later time.